Hey everyone, welcome. We're about to tackle a really fascinating puzzle today, grammar. It feels so deeply human, right? All that nuance and intuition. But what if a machine could actually learn it? So let's pop the hood and see exactly how you would build a machine that could master language.
So this is the big question, isn't it? How can a machine learn something as messy and, well, human as grammar? It sounds almost impossible, but computer scientists have been chipping away at this for decades. And to figure it out, we're actually going to build our own language learning machine right here, piece by piece.
All right, so any big project needs a set of blueprints, a plan. For our machine, those blueprints are something called grammar formalisms. This is basically the foundational rulebook that tells the machine what language even is in the first place.
And this is where things get really cool. Instead of just making a machine memorize an endless list of rules like a noun comes after an adjective, categorical grammars give each word a specific type. Think of them like puzzle pieces, literally. Every word has a unique shape. The machine's job isn't to memorize rules, it's to figure out how these puzzle pieces are designed to click together to form a complete sentence. It turns grammar into a kind of logical game.
Now, just like in real architecture, there's not just one way to drop the blueprints. And you don't need to memorize these names. The big takeaway here is just that scientists have come up with a whole range of different styles. Some are super rigid and logical, others are way more flexible. They're all just different attempts to find the perfect framework to capture the wild, complex structure of language.
Okay, so we've got our blueprints, but, blueprints don't build a house by themselves. You need an engine, something to do the actual work of learning from all that information. And in our machine, that engine is a learning algorithm.
This whole process actually has a name. It's called grammatical inference. This is the heart of our engine. It's the moment the machine stops being just a static model and actually starts learning, deducing the patterns and rules of a language all on its own.
So how does this engine really work? Well, one of the key methods is called unification-based learning. Think of it like a construction crew on a job site. Step 1. The crew gathers all the raw materials. The machine looks at a bunch of sentences that are already paired up with their pure logical meaning, like a computer-readable definition. From that, it starts to build a general list of word types. Then, step 2. The crew starts actually building. The machine takes all those different word types and starts unifying them, basically figuring out the most efficient way to fit them all together to build a compact, powerful grammar that can understand way more than just the examples it started with.
Okay, so check it out. We've got our blueprints, we've got a powerful engine, but that engine isn't going anywhere on its own. It needs fuel. And for a language learning machine, that fuel is, you guessed it, linguistic data. Lots and lots of it. And what this shows us is that not all fuel is created equal. The machine can learn from just raw text. We're talking billions of words scraped from the internet. And that helps it learn which words tend to show up next to each other. Or you can give it higher grade fuel. Expertly annotated data, called treebanks. That's where humans have already mapped out the entire grammatical structure of a sentence, basically giving the machine a perfect answer key to learn from. And then there's the premium stuff, sentences that are directly paired with their logical meaning. This teaches the machine not just how a sentence is built, but what it actually means.
We have the blueprints, we have the engine, and we have the fuel. Now for the last piece of the puzzle, the secret sauce, the fundamental principle that powers this whole machine and connects everything we've just talked about.
And here it is. This is the big aha moment. It's a concept called parsing as deduction. And what this does is totally reframe the whole problem. It says that understanding a sentence isn't just about following some rules you've memorized. No, it's about performing a logical deduction. The machine isn't just checking boxes, it's literally solving a logic puzzle every time it reads a sentence. I mean, really let that sink in. This is the core idea. Every time you or I understand a sentence, our brain is, in a weird way, finding a mathematical proof. And that is exactly what we are teaching this machine to do. This is the deep, profound idea that lets something as messy and human as grammar be understood in the clean, rigorous language of pure logic.
And listen, this isn't just some sci-fi theory. This entire field is built on a solid scientific foundation called computational learning theory. It's the branch of computer science that actually develops the algorithms and, get this, proves which kinds of grammars are even learnable by a machine in the first place. It's what turns these amazing ideas into something real.
So there we have it. We've built our machine. It's got the blueprints for grammar, an engine to infer the rules, and it runs on the fuel of human language. All of it powered by this deep, logical core.
And that leaves us with just one last big question to think about. If a machine truly finally masters the hidden logic of our language, what on earth will it say?